All right, we're going to go get started here in just a second. You hear me in the back there too? Sounds good? All right. OK, let's get started. So this talk is a deep dive on Rook. And my name is Jared Watts. I'm one of the founders and a senior maintainer on the Rook project. And I'm also a founding engineer at a Seattle-based startup called Upbound. And we are hiring. Said that in the last talk, too. So yeah, I think a number of you just came from the last talk. So you might be just as flustered as I am, where I just spoke downstairs somewhere. And then the escalators in this place, too, like you only have choices of going only up on one and only down on other ones. And they always have seemed that when I want to go in a direction, it's on the other side of the room. So I was like, all right, this is the direction the room is in, but the escalator's back that way. But we're all here, and that's good. So let's talk about what Rook is. We're not going to spend much time on that because you all were probably at the intro session yesterday. But let's do some level setting. So Rook is a cloud-native storage orchestrator. And what that means is that we've extended Kubernetes with new custom types and custom controllers in order to add a lot of software automation around operational tasks that a human would normally do to manage storage systems. So for instance, there's a number of tasks on the screen there about bootstrapping, configuring, deploying, managing, failover, all these sort of things. These operational tasks that have traditionally required a human operator to perform them. We can use software. We can automate those tasks with software and be able to make our lives a little bit easier. So in addition to being a storage orchestrator or a control plane for data services, it's also a framework for making the task of integrating new storage systems into Kubernetes environments much easier. We'll talk more about that in a second. So it's also an open source project, and it's hosted by the Cloud Native Computing Foundation. We first donated it to the CNCF back in January of 2018, and then we were graduated to the incubation level in September of last year. So let's talk a little bit more about that framework I was talking about. So Rook is more than just a collection of operators and custom resource definitions. It's also this framework that allows storage providers an easier job of integrating their storage system into cloud-native environments, such as Kubernetes. It provides a couple of different features to make that easier. One of them is like what we call storage resource normalization. And that means that there's a common set of specs and configuration and logic around what does it mean to declare a storage fabric. Lots of different storage systems need to be able to use a certain set of raw disks or persistent volumes or folders on host machines, whatever it may be. But you having a single common way to declare that the storage fabric for the underlying storage system and bring them into the cluster. There's the Rook Operators have the whole little framework around events and listening for CRDs and reconciliation loops in order to watch for new events related to storage and take action upon them. And then we have a big testing and integration testing environment that launches lots of different Kubernetes clusters across different versions of Kubernetes and perform testing and integration amongst those to make sure that storage is working. So this whole set of framework and specs and policy and testing, et cetera, can be used by different storage providers to make their job easier. So we have right now, Ceph is the first one that we started with. We started the Rook project with only Ceph. And so it is the most mature, it's the most stable, it has the most contributors. But we've also, since making this Rook framework, we've added new storage types as well. There's CockroachDB, MinIO, NFS, Cassandra, EdgeFS, and there's more on the way. So today, we're going to talk about some of the newer operators that I haven't yet had much of a chance until today to talk about. So I'm kind of excited about that. I also wanted to call out that the Rook project, we released 1.0 just a few weeks ago. And as part of that, there's a lot of features and code and whatnot that got included in that release. But one of my favorite things was actually the artwork. So all these cool little like night designs and stuff that we have in the slides. A designer named Chris did all those for us, and I think he did an awesome job with the artwork. And the stickers and T-shirts we had were gone within, I think, like 20 minutes or something like that. So either people liked the artwork, or we bought way too few stickers. But one of those is probably true. All right, so let's talk about the Apache Cassandra operator. So Cassandra is also an open source project, but it's a distributed NoSQL database. And so what I really like about Cassandra is that it can handle a large amount of data. You can throw a whole bunch of data at it. And because it scales across a whole bunch of cheap commodity hardware, you can just continue throwing cheap hardware at it. Instead of vertically scaling with expensive machines, you can horizontally scale with a bunch of less expensive machines. And then you get high availability, you get entirely super large data sets, and no single point of failure for that NoSQL database to die on, let's say. So Cassandra is a complicated system. Most distributed storage systems are complicated. The Ceph, that's complicated. That's why we started with Ceph. But Cassandra is not really that much less complicated, I would say. So I think it's a great candidate for building an operator around it, to be able to bring Cassandra into our Kubernetes clusters and have operational expertise in automation to manage it for us. So I definitely want to call out that the Rook's Apache Cassandra operator was designed and implemented by a guy named Yanis Arkadas as part of his graduate thesis. So I think that he did an awesome job with it, and he actually went and presented and defended his thesis about the Cassandra operator that he wrote. I didn't do anything nearly that cool when I was in school, so I think that Yanis is that was really cool for him to do that. And he's a very valued member of the Rook community now. And he was sponsored by a company called Arikto that has a booth here in the trade show floor. And Yanis actually works there now. I don't know, Yanis, are you in the room? He might not be, but he did a great job. All right. So Cassandra, the first question we want to ask is, do we need an operator? We could maybe just try to throw some StatefulSets at it and see if that can manage Cassandra for us appropriately. But there's a couple of different downsides to that. One is that the StatefulSet doesn't really give us a hierarchical topology model that we can use to define a complicated Cassandra cluster. With the StatefulSet, it just kind of confines you to one rack, and you can't do this different hierarchy and multiple racks and expand out the cluster that way. Another thing is that scaling down a Cassandra cluster, safely removing one of the nodes, is a process that you don't want to take lightly. You need to first decommission the node, and then you've got to stream all the data off of it to get it safely copied around the cluster, and then you let the member leave. So that's not really a great facility in StatefulSets to let you do complicated operations like that, in which you want to maintain the integrity of your cluster. And then there's other issues, too, with seeds and multi-zone deployments, backups, restores. The general extensibility of StatefulSets just isn't part of its design. So I think that makes a good case for Cassandra to get its own operator, which is why Yanis did that work. So let's take a quick look at this diagram here about the architecture or the setup here of the Cassandra operator. So just like any of the other Rook operators, it's sitting there in one of those reconciliation loops where it first observes the state of the cluster in the state of the desired state that the user has specified they want the Cassandra to look like. Then it does an analysis step where it compares what the user wants Cassandra to look like versus what's actually in the cluster. And then it acts to bring the actual state of the cluster in line with the user's desired state for their Cassandra. So let's think about how we model the set of concepts and resources in Cassandra. How do we model those to Kubernetes primitives that the Cassandra operator, can act upon? So let's start at the bottom. Let's start at just the individual members of the Cassandra cluster. We can model those with pods. Each member in the cluster can be mapped with a single pod in our Kubernetes. Then we go up from a single member to an entire rack of members, and we can model that with the StatefulSet. And so we're going to kind of keep expanding out here as we're moving along. And then if we move up to the data center, we can do that as a collection of StatefulSets, many StatefulSets working together to represent the racks and members that are part of a data center. And then finally, at the top, an entire cluster can be modeled with a custom resource definition, a CRD, that represents what it means to be a fully fledged Cassandra cluster. And you can tell that I didn't do this slide because it has animations. This is Yanis's slide. Mine are pretty broke looking compared to his. Oh, back to one of Jared's slides. OK, no animations. So the Cassandra operator, it's got a lot of neat functionality that Yannis coded into it. So the first one, obviously, is cluster creation and bootstrapping. Starting with a plain vanilla Kubernetes cluster, no resources, no Cassandra, the operator will take the steps to identify the storage resources that could be included in the cluster, be able to bring up members upon each one of them, have them start talking to each other and form a cluster. And then once you have a cluster running, it can do both scale up and scale down, where you add more resources, like a new node to the cluster or a new storage device, and you'll be able to grow that cluster, scale it up with more members, and basically that horizontal scaling we were talking about for Cassandra, the operator could do that for us automatically. And we also talked about scale down, too, and how important it is to do that safely, where you have to decommission the member, stream its data, and then allow the member to leave. The operator does all this for us in software automation. Another feature that I actually think that this one's sitting in a pull request and it's not part of master yet, so I don't want to mislead you here. That one is work that should be merged into master soon. But basically, when an entire node goes down, we have the Cassandra operator will be able to detect that and then take steps to bring up on the new node or a new node the members to replace them and rebalance the cluster and make sure that everything is happy. So being able to handle these failover scenarios where you don't have to get a human involved is really useful. And that really starts talking about or demonstrating the power of operators here and why we built a Cassandra operator inside of Rook. All right, now let's talk about EdgeFS. So these slides may be familiar to people that were at the last globally distributed global scalability talk that I just did on Rook. But EdgeFS is another storage system or a data plane that Rook provides orchestration services for. And so EdgeFS it's got a really neat architecture. So from the ground up, EdgeFS is natively designed to be globally distributed and globally scaled. And so the way it does that is that it works on a series of immutable blocks, similar to how Git works. And so when I say Git, I don't necessarily, in blocks for that, I don't mean blockchain, a chain of blocks, but I mean that blocks of data, that make up files, et cetera, are modeled and they are immutable, such that if you change a block in a file system or in a file, that block gets a whole totally new identity for it. It makes it globally unique. It's versioned, et cetera. And so that starts allowing the EdgeFS storage system to always have their caches at each one of the globally distributed sites to be in a consistent state. It allows global fault tolerance and global reliability and scalability as well. So for the terminology of EdgeFS, they're called segments. Like when you have a EdgeFS cluster here in Asia and an EdgeFS cluster in Europe, each one of those is the segments. And it's able to stitch those together into a single transparent geo namespace via what they call ISGW, which is an intersegment gateway. So they have these gateways that are connecting and linking all of the different EdgeFS clusters that Rook provides orchestration services for. So I think this is a really cool feature of EdgeFS and the EdgeFS operator, is that you can configure it to be in a metadata-only mode. And what that means is that, say you have one site in Asia, and then you want to also have another site of data in, let's say, Europe. So what you can do is that you can stream only the metadata of the files across the two sites. So I'm talking about what the file names are, the file structure hierarchy, like the file system tree, the sizes of files, the modification timestamps, et cetera. So you can stream all that across. And so if you think about it, metadata for files is like kilobyte size, right? And then the data itself is gigabytes or terabytes. So what this allows you to do is this allows you to almost immediately be able, on a different site, to start using the file system in a useful manner. Because you know what files are there, you know their timestamps, you know the whole hierarchy of them. You can start a client on another site can start fetching, reading and writing files, and the data's not even there yet. When the client wants to use one of those files, the data will be lazily populated or fetched on demand to start filling in that site. So it's not just, you don't have to wait for file A, file B, file C, and then finally file D. You immediately know that it's got files A through D, and you can ask for file D, and then that's the one that'll start streaming and using up bandwidth immediately. So it gets you the files that you need quicker. EdgeFS also does a global deduplication. So since each block has its own unique identity, and when you modify the block, it gets a whole brand new identity. We could do things like deduplication. If we've got multiple copies of the exact same data chunk, we're only going to store that one time, or store it as many times as we need to for the redundancy that we want. But basically, if you've got 3,000 copies of the same block, you don't have to duplicate it and waste all that storage space for 3,000 of them. You can make it much more constrained down to just the number that you need to maintain availability. And then another cool thing that EdgeFS does inside of Rook is that it's got built-in disaster recovery. So if you lose some data on one EdgeFS site or one EdgeFS cluster, then you can be able to recover that or fetch it from another cluster, another segment, completely transparently to the client or to the user, so that when they do a fetch, or sorry, a read for data that's not actually there locally, you lost it, the hard drive is gone, whatever it may be, it can fetch it from one of the other globally distributed sites, and there will be a little bit of loss in throughput necessarily, but you won't get an error on the client, you'll get that data back. And then your local cache then gets repopulated with that data and to recover automatically from the data loss that we had. All right. So those are the two new operators in Rook, or two of the newer ones. EdgeFS has been declared beta now with the Rook 1.0. So EdgeFS is maturing. It's got a good set of contributors working on it, and really happy with the progress for EdgeFS. And Cassandra, if we could get more contributors on that or get more Giannis's on it, then that would be awesome as well. We could continue to grow the Cassandra support as well. But it's a whole lot of really good support in the alpha version of Cassandra's operator. OK, so software in general runs in many different environments, right? Kubernetes itself runs great pretty much anywhere. You can, it's ubiquitous now, right? It runs in all the major cloud providers. You can run it on bare metal. You can run it on premises, things like that. Kubernetes is everywhere, and that's why there's like 12,000 people here in Barcelona, basically, right? I think Rook really shines the best in on-premises scenario. So for instance, if you're running on a cluster, you don't have access to EBS or to Google Persistent Disk, right? You don't have any of those nice cloud provider services. And so with the bare metal you have there, you can use Rook to orchestrate various sets of data services like Cassandra or Ceph or EdgeFS to give you highly reliable, highly available, durable storage, et cetera, services in your cluster. So Rook is great for on-premises. I think, though, that the cloud providers, their managed services that they run are great in the cloud. They have like a full team of engineers behind them, like with an SLA, et cetera. So the managed services that cloud providers write, those are good too. So we've got Kubernetes everywhere. We've got Rook is great on premises. We've got cloud provider services that are great in the cloud. But can we have both? Can we have all that together? Why do we have to settle for just one? So maybe we could manage our infrastructure, our platform services, our resources, our applications. Maybe we could manage those all from Kubernetes and from a single place. And now I say kube control, but what I really mean is the Kubernetes API, such that if it's in the Kubernetes API and integrated that way, you can use any of the tools in the ecosystem or libraries or frameworks or whatever to start managing all of these services. Kube control is obviously one of them, but the client Go or the REST API or web dashboard, if it's in the Kubernetes API, it's exposed in a uniform way across all of our surfaces there. Additionally, we could start defining some portable abstractions for some of our storage needs that go beyond block and object, or sorry, block and also containers as well. So let's talk about portability. So portability is important, I think, because if we're running in multiple environments or multiple clouds, et cetera, we want to be able to choose which one of those clouds or services that we're running in, right? We want to take our data wherever Kubernetes goes. And so I think that Kubernetes did a really good job at two different abstractions, the pod abstraction and the volume abstraction. So pods run containers, and that allows us to run our applications basically anywhere Kubernetes runs. And then volumes provide us with, if your pod needs persistent data, and all it needs is a file system or a block device, then volume is the great abstraction that Kubernetes made that your pod doesn't have to know where that data is coming from. It could be EBS, it could be an Azure disk, it could be Google Persistent Disk, or could have Ceph, RBD, it doesn't matter. The pod doesn't have to know, and the pod doesn't have to change either to use that volume, right? So those are great abstractions, pods and volumes. But applications are more than just pods and volumes, right? There's also databases, buckets, caches, message queues, AI/ML pipelines, all sorts of stuff, right? And so that's why we're also going to talk about and start showing you here some integration with Rook in this a new open source project called Crossplane that we open sourced in right before KubeCon Seattle, so about 5 months ago. So let's take this idea a little bit further here, make it a little bit more concrete. So everyone's familiar with storage classes and persistent volume claims inside of Kubernetes, right? So those concepts there, we can take those from volumes and apply them to the other types of storage. So a generalized resource class, similar to a storage class, can be thought of as a blueprint that would be created by the administrator. And then the administrator, they know all the environment details. They can set the policy. They own these clusters. So they can define these blueprints for how we might want to create an entire class of different types of storage, buckets and databases, et cetera, right? For example, a fast class, a standard class, a cheap class as well. And then very similar to persistent volume claims, we could do resource claims, general resource claims. So instead of just volumes, we could do claims for all these other types of resources that users can make to say, hey, I just generally need a Postgres database. Please give me one of those. And we can, the application doesn't have to know where it's coming from, just like an application or a pod doesn't have to know where its volume is coming from. A pod shouldn't necessarily have to know where its database is coming from. And so through these classes and claims, just like storage classes and persistent volume claims, we can start doing that on demand, not at design time or compile time, but at on demand at deployment time, your applications can get those resources that they need fulfilled. And now this is what I think really does enable portability across the different cloud environments and on premises. It gives us the power of choice. And this whole mantra of write once and run anywhere can really start becoming true, I think. All right, so that Crossplane project I was talking about, a multi-cloud control plane to be able to extend Kubernetes with the ability to manage multiple clusters, multiple clouds, deploy your platform services, your databases, et cetera, to any one of the cloud providers. Let's talk about what it looks like to integrate Rook with Crossplane and start doing new interesting scenarios, right? So Crossplane has some new functionality where you can extend it with out-of-tree functionality. So there's the main repo for Crossplane, and everything gets compiled in there and launched as a container, et cetera. But we can also, from the Rook project, we can compile and build functionality for Crossplane, and then install the Crossplane multi-cloud control plane that's spanning all of these cloud providers with new functionality such as Rook. And then that will give us the ability, which we'll see here, of how to dynamically provision all these new types of storage. And the key here is, since we're using Rook to do this, is that we'll be able to do this on premises as well. Because it's one thing to light up a database or a block volume or whatever in a cloud provider, but it's another thing entirely to be able to do that on bare metal, right? All right, so what we're looking at here is just some YAML saying it's an extension request to please take the Crossplane multi-cloud control plane and extend it with Rook's Cockroach operator. So we are going to look at some of the details about that. So CockroachDB, the Rook has an operator for Cockroach. We're going to look at the 3 steps of a traditional operator, the observe, the analyze, and the act step. But this is for dynamic provisioning of Cockroach, which implements the Postgres protocol on the wire. So here's some code. This is a deep dive, so we're getting into a little bit of Golang code here, not surface level introductory stuff. But basically, what I'm getting across in this slide here is that this step here is the observe step of an operator. So the important part is this line here, where we're setting up a custom controller for CockroachDB to watch for events on a general Postgres claim. So when a user says, I want Postgres, Cockroach is going to be watching here. Rook's Cockroach will be watching and ready for that. So the analyze step in this reconciliation loop is we see that there's a new request for Postgres inside of our local cluster here. And we're going to check and see, are we being deleted and handle that with the deletion function? Do we have a resource, a cockroach resource already created? If we don't, we're going to go ahead and provision it. And after all that's done, we'll bind the two together, the Postgres claim and the cockroach resource. And here's the final act step, observe, analyze, act. Act is when we actually provision and create the cockroach instance that will fulfill the request for Postgres. So we're saying here we're creating a CockroachDB cluster object, and we're calling create on the Kubernetes API to kick in the machinery of the regular cockroach operator. This is the cockroach operator part that provisions, dynamically provisions storage, and then the cockroach operator will kick in and bring up a whole cockroach cluster. So let's actually look at this thing. Let's see it in action. All right, and doing 2 talks in a row, I hope I don't confuse things. So I'm going to go back to this copy paste. This is not for you all. This is for me to copy and paste. And so what are we looking at here? We are looking at the Crossplane multi-cloud control plane. And what we see here is the main Crossplane pod is running. We can point it at any of the cloud providers, but we can also point it locally to the on-premises bare metal cluster. And bear with me here. When I say bare metal, what I really mean is my MacBook. But the concept is the same of on-premises, no cloud provider stuff involved here at all. The second pod we have here is the extension manager pod for Crossplane. So this is how we can build new functionality or integrate Rook into this multi-cloud control plane and open up new scenarios with this extension manager here. All right, so I'm going to do 2 commands here. I'm going to create a namespace, and I'm going to create a cockroach extension. So let's look at what that cockroach extension looks like. This should be familiar because it was on a previous slide of I'm asking Crossplane, requesting to extend it with Rook cockroach functionality. So this is how we're going to teach the multi-cloud control plane a new Rook cockroach trick. So we applied that, and so now what we should see is we should be able to check on our extension request. And the Rook CockroachDB package has been downloaded and applied to the Crossplane cluster, so it's ready to go. And then we can get more details, too, about the specific Crossplane extension, that it's ready to go and service cockroach requests. So another thing to look at here is that when we taught this multi-cloud control plane what cockroach and Rook really is, it also taught it some new CRDs. So now there's a new CRD for Rook's cockroach as well. This didn't exist before, but now it does because we extended the control plane with that. And then now, in addition to that CRD for cockroach, we also created a cockroach operator. So now we've got everything running up and running in the multi-cloud control plane here to start doing cockroach stuff. All right, so let's do cockroach stuff. And oh boy, I hope this is the right repo compared to the last demo. So and actually when I was practicing, I accidentally ran a kube control, like a Helm command on the wrong cluster. So I hope that did not mess up any of these clusters here. So we're going to see what happens. OK, so let's do first. Remember we were talking about storage classes and persistent volume claims, right? So resource classes and resource claims. Here, this should be very familiar to what a storage class looks like right now. But basically, we're declaring a Postgres resource class. And this is specifically for cockroach, right? So when somebody asks for Postgres, we're going to give them the local cockroach Rook implementation with various parameters here of just a gig because it's tiny, like 3 node, 3 replica count, how much cache to use, et cetera. But basically, that's the blueprint when somebody asks for Postgres that we'll be able to fulfill that with. And here's the final step to kick off this whole thing from end to end. So what I'm going to do is I'm also going to create the resource claim. So here we go. So the resource claim is a general Postgres instance. And I'm saying, please give me Postgres and use this resource class here, please, the Postgres resource class to fulfill that. The administrator has created a Postgres resource class that we just saw. And now that we're going to ask for Postgres, and we're going to get cockroach in response locally on our bare metal cluster. So let's look at it. Did that work? What happened? Cool. It does look like it worked. So we asked for Postgres. We got Cockroach. We have a 3-node Cockroach cluster orchestrated by Rook, up and running and ready to do stuff. And notice we did this all in a generic way the entire way. We could have asked for Postgres, and we could have gotten Cloud SQL if that's what our administrator had made the choice of. If their resource class said use Cloud SQL instead, that's what we would have gotten. So for instance here, we asked for Postgres, and it's bound now. It's bound to oh boy. The Postgres instance is bound to the Cockroach instance, just like dynamic provisioning for volumes. All right, so let's use the thing. Cockroach should be up and running, so I'm going to exec to it, and we got a beautiful Cockroach interface here, where I'm going to say, show me the databases. And this shows that we have a system database up in provision. The 3-node Cockroach cluster is up, running, talking to each other. We've got data. We've got Postgres. We've got Cockroach. So now let's start feeding data into it. So I'm going to start up a load generator program here that's targeted at Cockroach. And so this is going to spin up a pod that's just going to keep writing random data to the Cockroach cluster. And if we look at the logs at it, it's doing write operations. It's doing benchmarking. It's testing the speed and throughput. And if we actually do a database query, we can look at that data that it's throwing into Cockroach right now, too. So basically, we see here that to throw it all together and wrap it up here, we asked for Postgres in a general way through a resource class. That was the administrator specified that should be Cockroach with Rook on a local cluster. And with the Crossplane multi-cloud control plane, we get all this put together so that our general resource needs are now portable, and we can do databases, caches, object storage, message queues, all sorts of stuff in general ways, just like we can do with volumes. All right, so let's switch back to the slides here. And quick summary. We covered that Rook is a cloud-native storage orchestrator. You should know that by now. And then we have a framework here that has enabled new operators like the Cassandra operator and the EdgeFS operator, storage services inside your Kubernetes cluster orchestrated by Rook. And we also learned how we can extend Crossplane's multi-cloud control plane with new functionality to deploy new types of resources in addition to volumes that we already have already in the cloud and on premises. Rook and Crossplane are both open source projects. We have 150 or plus contributors on Rook. We want more always. We're growing the community. I'm really happy to see all of you guys here, and probably a lot of you were at the intro yesterday, active on Slack, Twitter, etc. Please join us. And we have a couple more sessions at KubeCon today. They're all today. There's a Meet the Maintainer session that starts in 2 minutes. Oh, damn. Excuse me. So we'll be down at the CNCF answer bar to be answering questions down on the trade show floor. And then we also have a couple more talks later on today. And I think that would be, thank you very much. I appreciate it, everyone. So I think, yeah, if anybody does have questions, I think we have 2 minutes or so, as I've stated, before we go down to the CNCF answer bar. Yes, I think I saw your hand first. Yeah, so the question, I think the question was if there's actually enough code out there to take that database CRD and start using it on premises and across all the clouds. So what I showed here, all the cloud ones are available. Like those are part of the Crossplane project, so you can do MySQL and Postgres, et cetera, across Google, Amazon, and Azure in a general way. But this local Rook in cluster on premises functionality is still in a prototype thing. I was coding some of it last night actually, so that should be coming soon. Yes?
Two quick questions. So first of all, now that you are no longer just a self-operator, but more of a framework thingy, are you also planning to support out-of-tree plugins or out-of-tree operators?
That's a great question. So the question was, since Rook supports more than just Ceph now, it supports multiple types of storage systems and operators, if we'll be able to enable out-of-tree operators, et cetera, for Rook as well. And that's a good question because we're starting actually to feel the pains now of having everything in tree and having to manage releases for multiple storage systems and get everyone coordinated and get the code out, all on the same day and all that stuff, and tying storage systems, tying their release dates to Rook release dates. We're feeling the pain of that right now. And Kubernetes did the same thing with all their in-tree storage plugins, and they moved to an out-of-tree model as well. So I think we're kind of moving towards there yet. We haven't done it yet, but we're starting to feel that pain. And that's going to be something that we need to discuss as a community and find out the right solution that works for everyone. And so we have community meetings every other Tuesday, and that's a great topic that we'd be able to talk about there. So, oh yeah. Yeah, so there is local PV support. So in the Rook framework, you can specify what storage you want to be involved in the cluster. And so there's all different types of ways to pick and choose that storage. And one of them is persistent volumes or local PVs as well. So you can include those as part of your storage system. Yep. And do you have a question too before we have to go to the CNCF bar?
Okay, so it might be that it's just been answered with the local PVs, but how do these operators work with cloud, ephemeral, and VME storage?
Yeah, so the question is, how do these operators work with cloud and local and ephemeral NVMe storage? We wrote a blog post maybe a year or so ago about running Rook in Amazon with a EC2 instance using instance storage, which is locally attached SSD drives, and the performance benefits you get from it, the cost benefits. It was actually a pretty compelling story where you got really good throughput, you got really good cost as well, and it was compared very nicely to what you get in EBS. The Rook as an orchestrator in all these different storage systems as data planes, they can use anything they want. Have that common code to specify and pick up and absorb all these volumes and devices, et cetera, into your cluster. And so that means too, in the cloud, you can do the same thing. Whatever's on your cloud instance, you can suck that up into the cluster and include that. The question where it gets kind of interesting though, is that in the cloud for using EBS, you've got a whole team of engineers in Amazon that's managing it. There's an SLA. Maybe EBS isn't the best example because I think everyone has their own EBS horror story. But in general, you've got a whole team managing it. When you're running your own Rook cluster inside of a cloud provider, definitely you can do it and you get good results. But still, at the end of the day, it's your responsibility. You're managing that cluster. You have to be on point and on call for making sure it's working. So that's the trade-off. Cool. Thank you. I get going down to the CNCF answer bar now.